Whoop. Hey everyone, it's Mr. Canfield. We're going to be doing u-substitution, so we're going to do u-subs part 2. Alright, so some people call this u-subs instead of u-substitution. So anyway, we did the first 8 examples in the last video, and we're going to do the second 8 examples in this video, plus 2 more. I guess that'd be 10 more examples. So we got number 8, so we're going to start with number 9, and I'm going to review the concept of u-substitution, and then we'll handle number 9. Now, number 9 is actually a really perfect one for us to be starting with today because comparatively to the previous few, this is a little bit simpler. Okay, so let's see. I need to move my camera a little bit. There we go. Okay. So, the idea of u-substitution is if we have an integral that we can't use our standard power rules on, there's a way to still go through and solve that integral, to take the integral. So, in this situation, we know the antiderivative of x. We know what we took the derivative of to get x. So I don't actually need any special fancy things for it. However, the square root of 3x, if this had just said the square root of x, I would know how to do that. We'd be able to use our exponents and do things to it. But since we don't have that, we're stuck. So what we're going to be able to do is we're able to separate this into 2 separate integrals and say it's the integral of x dx minus the integral of the square root of 3x dx. And so our first integral here, easy peasy, it's x to the 1 right now. We add 1 to our exponent, get x to the 2, and then divide by our new exponent. And you could put a plus c here, but I'm just going to put 1 plus c at the very end when we're finally done. Minus the integral of the square root of 3x dx. So the square root of 3x dx is where there is actual work to do in this problem that uses u-substitution. So the idea with u-substitution is that, okay, I have, instead of dealing with the square root of 3x, let's call it the square root of u. If only I had like the square root of u du, well then I'd be able to go, oh, well, I know this is u to the 1/2 du, and so to do my integration here, I add 1 to the exponent, I divide by the new exponent. So if only there was some way to kind of think about this in different terms. And so what we do is we make a substitute. We say, hey, instead of 3x, basically, instead of the thing inside there, let's just call that u. Oh, I wrote that on the opposite side. I normally will write u equals 3x. It doesn't change what it means. I just want to be consistent. So then I take the derivative of this. I get du dx is equal to 3. And so the reason that I'm doing this is because there's a dx, and this is like u and x, and I want to see if I can make a dx and solve for a dx. So the way I do that is take the derivative. It makes a du over dx pop out. And then we can multiply both sides by the dx, and then divide both sides by the 3, and get dx is equal to du over 3. And so I can go back in here, and I can substitute and say, instead of saying the square root of 3x, I can now say it's the square root of u. And instead of saying dx, I can say du over 3. And so remember, this is really 1/3 du, so I'm going to pull the 1/3 out front of the integral. It doesn't affect anything inside. And instead of saying the square root of u, I'm going to say u to the 1/2. So now when we do our integration, u to the 1/2, we add 1 to that exponent. So 1/2 plus 1, it's 2 over 2, right? We add 2 over 2. We get 3 over 2. So we get u to the 3 over 2 with a negative 1/3 out front. And remember that we multiply this by the reciprocal because we're dividing by it. Divide by a number is the same. So dividing by 3 over 2 is the same as multiplying by 2 over 3. So I'm just going to drop this down. We got our x squared over 2 minus 1/3 times 2/3 times u to the 3/2 plus c. And the only thing left to do is to resubstitute back into u what u actually is. And no, that's not improper grammar. what is u? It's a silly question to ask someone. So instead of writing u, we write what u is, which is 3x. And so, yeah, it looks terrible, but the u substitution hopefully is clear. All right, let's keep going. Number 10. Cool, nice and easy. Number 10. Number 10 says, take the integral of the square root of x squared minus 1 dx. All right, so you're going to watch me struggle a little bit here. I'm going to choose a u that I know is not the right u, and I want to show you what happens if we run into that. I'm going to say u is equal to x squared minus 1. Here's how I know this is the wrong u. When I take the derivative of this, if you remember last time when we were doing these, a lot of the derivatives we would take would leave something over in the derivative that we see somewhere else in the problem that gets canceled out. When I do this substitution at the outset, I have the square root of u, and the dx is going to get replaced with stuff, but there's nothing else to get canceled. And so this is going to cause us some problems. Let's see, du dx is equal to 2x. So then du over 2x is equal to dx. You know, I multiplied by the dx, then I divided by the 2x. Here's the problem. The problem is I still have an x. I can't do u substitution if there are any x's left. So this tells me this is likely not the correct u substitution to arrive at an integration that works. So instead of trying u equals x squared minus 1, I freaked out for a moment when I looked at this and I said, I can't think of anything else. And then my brain said, well, you could try factoring. And the other part of my brain goes, well, what good is that going to do? Well, let's just see what happens. This is definitely a more challenging scenario, but not impossible. Not impossible. So instead of writing x squared minus 1, let's factor that to x plus 1 times x minus 1. Which at first glance you might say, well that doesn't help anything, and it very well may not help anything. So I'm going to say u is equal to x plus 1. So if I go in and do my substitution, let's see, so du dx is equal to 1, so du is equal to dx. So if I go in and do my u substitution, then I wind up getting the integral of the square root of u times x minus 1 du. I still have an x there. Well, if x plus 1 is u, then couldn't I rewrite this and say that if u is equal to x plus 1, if I solve this for x and get u minus 1 is equal to x, couldn't I say this is the square root of u times u minus 1 minus 1? Like where x is, replace it with u minus 1. So u minus 1 here, and then minus another 1. Or u times u minus 2 du. Like, this is valid. Let's see, then I get, if I multiply that out, I get u squared minus 2u du. Cool. That doesn't help. I don't know what to do with this either. What to do. I'm going to pause real quick. Okay, so I just wanted to double check that. So I thought this was what it was, but so The only method that we have to do this is not covered in this course. It's called integration by parts, if I remember correctly. But regardless, Stu gave us this problem so that we could see sometimes even u-substitution using this tool. By the way, this other thing I did down here, this was some next level stuff. This would really kind of be my expectation that you would have thought through yourself, and the fact that we have x's and u's mixed. In case you don't know, u and your x don't mix. So the fact that you and your x are still here together, that's not okay. So stupid joke, but maybe helps you remember that this is not an okay situation, and neither are these. So for now, we don't know how to do this. If you want to see what we can take the derivative of to get it, sorry, it's this. It's x root x squared minus 1 minus the natural log of the square root of x squared minus 1 plus x all over 2, and we'll have plus c on the end. So yeah, if you really wanted to know, it's that. So hooray, isn't that great? All right, 11. Back to ones that we're able to do. All right, 11 says the integral of the cosine of 4x. Okay. I'm going to do this two ways. I'm going to do this using u-substitution, and then I'm going to do this using essentially u-substitution, but a more intuition-based u-substitution with less writing. So I'm going to say, okay, make the inside u, right? U is equal to 4x. That makes du dx equal to 4, and then we'll multiply by the dx. And then we'll divide both sides by the 4, so we get du over 4 is equal to dx. So when I go up here and I do my replacement, I get cosine of u du over 4. I can pull the 1/4 out front. And hey, what did I take the derivative of to get cosine? I took the derivative of sine. So it's sine u with that 1/4 out front plus c. And in class, a lot of people were struggling back and forth. Hey, wait, is it plus, is it negative? Is it plus, is it minus? Like, which sign do I put on here? Just think for a moment, take the derivative of this. Do you get back to the previous line? If you get back to the previous line when you take the derivative, that's the correct sign on there then. The correct plus or minus. And then at the end, we'll just drop the 4x back in. All right, so here's how I would do this problem without u-substitution. And I'm going to do a slightly different problem, a way slightly different problem. I'm going to do the integral of secant squared of 5x dx. Whoa, it's so different. And my joke by saying, whoa, it's so different, in case you're missing it, is the derivative of something is secant squared. One of our 6 trig functions, we take its derivative, we get secant squared. That happens to be tangent. So the way that I do these is, if it's just if it's a simple thing like a 5x, like some constant times x, or even it had been like 5x plus 1 or something. All I do, I'm going to actually make this 5x plus 1. I know that if I took the derivative of tangent 5x plus 1, take the derivative of this, right? The outside changes to secant squared. What's the inside do? It stays the same. The only extra thing when we take the derivative of this is the derivative of the inside pops out front. So a 5 would pop out front. And so if I took the derivative of this as I see it right now, I would get 5 secant squared 5x plus 1. So if we go look at the original here doesn't have that 5 out front. So that means what would need to be here so that when I take its derivative and get 5 secant squared 5x plus 1, what would need to be here so that when the 5 pops out, it cancels and we're just left with a plain secant? A reciprocal of this, a 1/5 would need to be out front. And so these it's possible to do these in your head without doing u-substitution. So everybody thinks about these differently, but yeah, you can do these in your head, theoretically. All right, let's look at 12. So 12 says, take the integral of 3 sine 1 minus 3x. All right, let's see. So in this situation, you could pull the 3 out front. And I'm already thinking I'm probably going to make the inside there u. So I'm probably going to make it like 3 and then sine u. I just have to figure out what's going to happen with du and everything. So it's good for us to do our side work. U is equal to 1 minus 3x. So if you're interested, I would recommend trying that technique I mentioned before. Great way to do this problem. So, excuse me. But I'm going to show my u-subs work because I'm trying to make these helpful notes. So my du dx is equal to negative 3 because we take the derivative and then we'll multiply both sides by dx and then divide by negative 3 and get du over minus 3 is equal to dx. So if you were predicting that we were going to have a negative 3 there, you can see that the 3 and the negative 3 are going to cancel each other, and we're going to be left with a negative sine u du. And so remember, when we think about what we took the derivative of, we take the derivative of cosine and we get negative sine. Well, this is already a negative. So then that means we took the derivative of cosine and we got this. So cosine of u plus c. So then let's see, cosine of u, we'll just drop our u back in. So cosine of 1 minus 3x plus c, and we'll call it a day. All right, let's see, 13. Oh, good. 13 looks nice, relaxing, calm. Don't even need a new piece of paper, clearly. All right. Sine cubed x cosine x dx. These look so much worse than they actually are. But, you know, visuals are oftentimes 90% of the battle. So I actually have a preference for these, a way to kind of visualize what's happening. Remember that sine cubed x means sine of x, the quantity, cubed. So if we're thinking about it like this, this makes it much more obvious what our u value is going to be. So I actually could make u cosine or sine, but because if I make it cosine, then negative sine is the derivative and it's there. Usually you want to do the one that's inside of other stuff. So I'm going to make the insides this sine. I'm going to make that u. So if I make sine u, let's see, then du dx is going to be cosine x, and then we'll multiply the dx over here, and we'll divide by the cosine. So du over cosine x is equal to dx. And this actually turns out to be a really, really nice u-substitution, because we just write u cubed, and then I can put du over cosine x here. Get canceling, and we get u cubed du, which is like, that's like a present. You know, we started with this monstrous looking thing, and we end with, oh, u to the fourth over 4, right? We add 1 to the exponent, divide by the exponent, plus c. End the day, drop u back in, sine x to the 4th over 4 plus c. You wouldn't see it like this as an answer, though. You would see sine to the 4th x over 4 plus c. So it's pretty awesome. But yeah, so the key thing about seeing this is to go, oh, I've got sine cubed and cosine. This looks scary. Wait a minute. Sine cubed x means sine x cubed. this inside's here. That's most likely what I'm going to want to make as u. And then its derivative is present. So let's see, 14. 14 is honestly, I think, a little bit more obvious than 13 was. The mechanics of it are slightly more involved, but the visuals on this are a little bit easier. If I think about it, the derivative of cosine is negative sine, but I have 1 minus sine. You know, I can think about that as 1 minus sine, the quantity. So I don't see its derivative present, but I do have 1 minus sine, and the derivative of this is negative cosine, which we essentially see here, just with a coefficient. So because of that, I'm going to say u is 1 minus sine x. So when we take the derivative, we'll get du is equal to, sorry, du dx is equal to negative cosine x, and we'll multiply the dx over here and divide by the negative cosine x. And so then when we go in and we do our replacement, well, this is great. And here's the thing. When I do problems like this, I don't often write this step here when I'm doing my own work. What I do is I like to see, I'll go, oh, du is equal to cosine x. So if I just move the negative 1 over here and make it negative du, then I can replace cosine x and dx with a negative du. And so I'll be able to say that this is going to be negative square root of u du. It saves me writing. I did not teach this until last year when a few of my students said this is how they were thinking about it and they really prefer it. So if you prefer this, that's awesome. If you're able to see shortcuts, do the shortcuts. There's so much work in this course as it is. You know, making less work for yourself is fantastic. So anyway, if you were to do the regular u substitution where we leave everything the same, change this to u, change this to negative du over cosine x, you'll see that the cosines cancel and the negative can get pulled out front. So we get the same thing. And now we'll just do our normal raise the power by 1. So u to the 3/2 multiply by the reciprocal and then plus c. So what is that? Negative 2/3 1 minus sine x to the 3/2 plus c. And call it a day. 15. So 15 is another one that I legitimately would not do u substitution. It's tan 10x secant 10x dx. The thing that I should recognize here is that it says tangent 10x secant 10x. Wait, that's like tangent x secant x, or secant tangent x. Its antiderivative is just secant of that. If I take the derivative of this, I get this. Except if I were to take the derivative of this because of chain rule, that 10 would then pop out. So to make a 10 that's going to pop out, to like pre-cancel that 10, I've got to throw a 1/10 out front. And so I can get my answer without doing any work. The work version of this is to say, well, let's set the insides equal to u and then take the derivative and get 10. So du over 10 is du. So if I were to do the u substitution here, we'll get, the reason I'm taking it and actually doing it this time is because of the, there's 10x and then 10x again. So it's going to be tan u secant u. And then replace dx. Oh, I wrote du over here. Replace dx with a du over 10. So then we're gonna, go through and do the work. There's the 1/10 out front. Turns out to be, the same thing. So, okay. On to number 16. All right, 16 is the next. This is the next one that I've seen that I'm like, okay. All right, let's see if we can't find a way to do this. All right, so tangent squared x secant squared x dx. Aha! Okay, so I figured this out, and I'm going to show you how I figured it out. So what I did was, that first thing I visualized was, oh, this is like tangent x squared. And before I even got here, I was like, wait, what's the derivative of tangent? It's that. So, you know, you could have been like, well, tangent x squared and secant x squared, and then thought about, okay, what's the derivative of this? What's the derivative of this? And it turns out the derivative of tangent x is secant squared, and so there's our winner. So I'll say u is equal to tangent x du dx is equal to secant squared x, and then I'll multiply the dx over here, and I'll divide both sides by secant squared. And yeah, dividing by secant squared, you could multiply by cosine squared instead, but I'm trying to cancel things out in the original problem here. So I want to do things that are going to make my life easier. So when I go through and I do my u-substitution, here I'm gonna cheat just a little bit. I'm just going to show you guys. I already know the answer to this is going to be tangent cubed x over 3 plus c. And I did that by recognizing this pattern and kind of running through the u-subs in my head. I'm saying that because I think some people in our class are capable of doing that thing, and you might be capable of it too and just not believe that you are. So if you go like, oh wait, yeah, this is u, I start with a u squared, everything else is going to go away, I'm going to add 1 to the exponent, divide by the new exponent, and then drop the u back in. That's the whole process. All right, so anyway, enough future telling. So I'm going to replace tangent x squared. We'll replace the tangent x with u and call this u squared times secant squared x. And then instead of writing dx, we'll write du over secant squared x. Hey, look, the secant squareds cancel out. We're left with the integral of u squared du. Take the integral, add 1 to the exponent, divide by the new exponent, plus c, drop tangent back in, and we're done. The most frightening problem to me today was this one when I saw it. And the trick for me was breaking down my trig, looking at what was actually going on, remembering my trig derivatives. And it's not magic to remember them. Please hear that. It's not anything special to remember these things. All right, 17. 17 and 18 are more advanced, and we'll talk about how to handle them. So in 17, if I were to make, I view this as the inside. If I make this equal to u, let's see, u is equal to x minus 4. We do run into a problem. du dx is 1, and du is equal to dx. This x plus 2 does not get replaced. And if I go in and I go, hey, I have x plus 2 times the square root of u du. Remember, u and your x don't mix. And that's for the best. And so because of that, we have an issue, and we're stuck. But something that you can do is you can go back here and you can solve this guy. You can get x by itself and say, well, u plus 4, add 4 to both sides here, is equal to x. You can go up and do a substitution here. And so it's a slightly different u substitution, because we're replacing one thing just with u, figuring out how du comes in, and then we're replacing this x with a u plus 4. So think about that, u plus 4, then plus 2. So that's going to be u plus 6. And you might look at this and I would imagine, if I was a student, I would look at this and I'd say, well, that's worthless. Sure, there aren't any x's, but like I'm no better off than I was here. And that is where you're wrong. There's actually something really cool that we can do with this. And by cool, I mean like something really, we can get to the answer with this. So u plus 6, and let's, instead of writing square root of u, let's call it u to the 1/2, right? So this is a parenthesis, or sorry, this is like a binomial inside parentheses. We can just distribute the u to the 1/2 to both of those. This is u to the 1 times u to the 1/2. In case you don't remember, when we multiply, and it's two different exponents with the same base, we just add the exponents together. All of a sudden this turns into u to the 1 plus 1/2, which is 1.5 or 3/2, plus 6u to the 1/2 du. That's nothing. I add 1 to each exponent, right? I get u to the plus 2 over 2, 5 over 2, divide by my exponent, and then 6u, add 2 over 2, get 3/2, and then divide by my exponent, multiply by the reciprocal. Ooh, 6 and 3, 6 will turn into a 2. I'm left with 2u to the 5/2 over 5 plus 4u to the 3/2 plus c. And that, let's see, u was x minus 4. So this is often called double u-substitution. It's not called W substitution. It's called double u-substitution. Number 18, x squared over square root of x minus 1. Okay. All right, with 18, you probably are going to want to make x squared equal to u. So let's kind of tease this out. This is, from experience, I already know what's going to happen with this problem. I've done enough of these to go, oh, this is one of those. But let's kind of go with our gut. Maybe your gut is actually to make x minus 1 the u, and in that case, that's awesome. That's the correct gut. But I'm gonna go with the gut that I would have had as a student, and that's, let me make u equal to x squared, because when I take the derivative of this, I get 2x, and I see an x. I'm like, oh, maybe there's some kind of interaction here. So we'll do the normal solving. Du over 2x is equal to dx. And I'm going to go in and do my substitution. I'll get my u on top, and I'll get my square root of x minus 1, and then I'll get my du over 2x. Oops, not dx, 2x. And we're here, and nothing. Well, maybe I could say, like, well, u is equal to x squared, so then I could say that the square root of u plus or minus is equal to x, and then I could have the square root of the square root of, no, I'm just kidding. No. Okay, so this isn't working. Maybe this isn't the right u. Maybe I should make u equal to x minus 1. And initially, you might say that's a bad idea. Okay, du is equal to dx, and so, sorry, take the derivative, you get du dx is equal to 1, then multiply. Yeah, okay, so let's try this substitution. X squared, square root of u, du. Still have an x squared there. Oh, right. But I could get u by, or I could get x by itself here by adding 1 to both sides and saying u plus 1 is equal to x. And then I could plug in and get the integral of u plus 1 squared over square root of u du, which you might think, no, this is bad. This is even worse than it was before. Why does life hate me? You know, like, what's, oh, no. But just pause. Let's FOIL that numerator out. U plus 1 squared is equal to U plus 1 times U plus 1. So we get U squared plus plus 1U plus another 1U plus 1. So I'm going to write U squared plus 2U plus 1 over U to the 1/2 du. If you don't see it yet, the reason why this is good is because now we can take this and we can break it apart and we can write this as the integral of each of these divided by U to the 1/2. U squared for U to the 1/2 plus 2U for U to the 1/2 plus 1 for U to the 1/2 du. And if we simplify each of those, we subtract those exponents. 2 minus 1/2 is 3/2. Still haven't taken the integral yet. I need to leave it out there. 1 minus 1/2 is 1/2. Then this is just plus U to the negative 1/2. Now I can take I almost said derivative. Now I can take the integral of this and get U to the 5/2 times 2/5. Remember, we're adding 1 to that. Then add 1 to this and get 2U to the 3/2 times 2/3. Am I on screen? Dang it! Sorry. Then plus U to the, we'll add 1 to that, get U to the 1/2 plus C, times 2 over 1. So final answer, I'm running a little bit low on space. I'll write it over here. Final answer, 2 5/2 plus, I actually forget what U is right now and I'm not looking, plus 4 over 3 U to the 3/2 plus 2 U to the 1/2 plus C. All right, so U was x minus 1. Did I draw a happy face or a sad face? Happy face. Okay. So, if you felt like u-substitution was easy, that's awesome. Most people don't. Most people really struggle with u-substitution. But hopefully this video walking through it was helpful, and hopefully practicing these homework problems will give you a chance to get used to the mechanics, so you can, just bust out good grades and stuff. I mean, learn, all about learning. Bye.